Okay, let's dive into this. Welcome, everyone. If you're studying mechanical engineering, manufacturing, or you're just diving deep into the world of CAD/CAM, you already know one universal truth. A machine tool is really only as good at the cutting edge doing the actual work. Today, we're taking a micro to macro journey into cutting tool design. We're going to start at the absolute fundamental geometry of a single microscopic cutting edge, and then we'll build all the way up to full CAD design and real-world CNC execution. It's going to be a fun one. So here's our pedagogical roadmap for today's explainer. We'll cover tool geometry basics, form and special tools, gear and spline machining, broaching principles, the calculation and CAD workflow, and finally wrap up with CNC efficiency and optimization. All right, kicking things off with Section 1, Tool Geometry Basics. Before a tool ever touches a workpiece to remove material, we really have to analyze it in its static state, treating it strictly as a geometric body. The absolute most critical parameter we need to understand here is the rake angle, which we denote with the Greek letter gamma. This is the angle between the tool's rake face, that's the surface the chip physically slides across, and the base plane. This specific inclination is absolutely vital because it directly dictates how the material deforms, the cutting forces involved, and the flow of the sheared chip right out of the cutting zone. Think of it this way. A positive rake makes the tool sharper, while a negative rake makes it stronger. Now, what's really interesting about this slide is that to accurately measure that rake angle, and literally every other angle on the tool, we have to establish a strict 3D coordinate system. These intersecting reference planes, like the base plane and the cutting-edge orthogonal plane, form the foundation for all 3D engineering calculations. Without standardizing these planes, well, a manufacturing engineer just cannot accurately design or grind a tool to repeatable specifications. It's like trying to build a house without a blueprint. Okay, once those planes are locked in, we can define the rest of the fundamental cutting angles. Aside from the rake angle, we've got the clearance angle, alpha, which essentially prevents the back of the tool from rubbing against the freshly machined surface. Then there's the wedge angle, beta, representing the physical bulk of the cutting edge. Mathematically speaking, in the orthogonal plane, the rake, clearance, and wedge angles must perfectly equal 90 degrees. Calculating these correctly is the ultimate balancing act. You're trying to prevent tool failure from a weak edge on one side and workpiece damage from excess friction on the other. Let's shift gears a bit. Section 2, Form and Special Tools. Zooming out slightly from those basic angles, you'll see that in any real-world manufacturing environment, you have standard, off-the-shelf tools. Those are great for general-purpose, straight-line machining, high availability, all that good stuff. But then you have non-standard or special-purpose tools. A form turning tool is a perfect example of this. It has a completely custom-designed profile engineered to cut a specific, highly complex shape into a workpiece in just a single radial plunge. As an engineer, you often have to design these entirely from scratch because your exact workpiece profile simply doesn't exist in a standard catalog. And designing that form tool requires some rigorous analytical calculation. Looking at the data mapped out here, you realize you can't just copy the workpiece shape one-to-one. No way. Because of the clearance and rake angles we just discussed, the actual depth and angle of the tool profile must be mathematically adjusted at different nodal points, like points 1, 2, and 4 right here, to ensure the final cut dimension on the circular workpiece is perfectly accurate. It's a real puzzle. Moving on to Section 3, Gear and Spline Machining. Now diving into highly complex, multi-tooth tools, and this brilliantly illustrates how we create gears. We have two primary methods here. Gear hobbing uses a continuous, synchronized rotational cutting motion between the hob cutter and the gear blank. It's almost like a worm gear driving a wheel, except, it's slicing through metal. Gear shaping, on the other hand, uses a reciprocating up and down cutting motion. While hobbing is incredibly fast and progressive, shaping is absolutely essential for cutting internal gears or for working right up against a shoulder, where a massive hob cutter just wouldn't fit. When designing a gear hob, precision is quite literally everything. Take this specific number, 25.13 millimeters. This is the exact normal pitch calculation for a single-thread gear hob cutter designed with a module of 8. By multiplying pi, the module, and the number of threads, an engineer determines the exact spacing required on the cutter to generate a flawless gear tooth. We see that exact same level of mathematical rigor in spline hobbing. If you aren't familiar, splines are essentially ridges on a shaft that mesh with grooves in a mating piece, perfect for transferring massive amounts of torque. The profile of a spline hob must be meticulously calculated. Engineers often use what's called the replacement arc method for this. Why? Because you have to guarantee that the final machine spline shaft fits perfectly into its mating component with absolutely zero slop. Next up, Section 4, Broaching Principles. Okay, broaching has to be one of the most fascinating processes in manufacturing. It is an incredibly efficient method of sequential material removal. Just imagine a long bar with a huge series of cutting teeth, where every single tooth is just a tiny fraction of a millimeter taller than the one before it. As the broach is pulled linearly through a starting hole, it progressively shears away material tooth by tooth until the final dimension is achieved. The real magic of a broach is that it combines roughing, semi-finishing, and precise final finishing all in one single powerful stroke. All right, Section 5, Calculation and CAD Workflow. Let's move to and see how this builds into the practical day-to-day engineering design process. How do we take all this dense geometric theory and turn it into reality? Well, it always starts by defining the workpiece requirements and selecting the tool type. Next, you calculate the cutting parameters and geometry, like our trusty rake and clearance angles. Then you draft the precise 2D technical profile, baking in all those tight tolerances. Finally, you jump into software to develop a full 3D CAD model, letting you verify the design virtually before you ever dream of cutting into a piece of expensive tool steel. Actually, a quick side note here. While designing that CAD model, it's so easy to get completely fixated on just the cutting edge. But remember, a tool consists of two main parts. The holder, or shank, is equally vital. If the dimensional tolerances of the shank are off, you simply won't get rigid integration with modern CNC machines. And without rigidity, you get chatter, and chatter destroys both the tool and the workpiece. Finally, Section 6, CNC Efficiency and Optimization. Let's pull back to the macro view and look at how perfectly designed tools actually perform in the real world of smart manufacturing. Industry experts identify 7 core methods to maximize CNC efficiency. Sure, you absolutely must start with high-quality cutting tools, but that is just the tip of the iceberg. You need flawless CAD to CAM software integration, you need optimal cutting speeds, the right cutting fluids to manage heat, and strict routine machine maintenance. At the end of the day, a perfectly calculated tool will still fail if you don't manage chip removal, or if your factory's manufacturing execution system isn't accurately tracking machine health. To really anchor this theory in reality, let's look at a specific optimization study. This uses the Taguchi method for turning SUS 304 stainless steel, which, if you've ever machined it, you know is notoriously tough. Through rigorous experimental analysis, engineers found the exact optimized geometry to get the absolute best surface roughness. Notice how the rake angle is -5 degrees, combined with a highly precise 0.4 millimeter nose radius and a -6 degree elevation angle. So, the crucial point is the distribution of influence. When evaluating which of those geometric parameters had the biggest impact on the final surface finish, the rake angle accounted for a massive 65% of the influence. It literally dwarfs the nose radius and elevation angle. This proves exactly why we spent so much time defining those basic coordinate planes at the start of this explainer. If you get the rake angle wrong, you ruin the entire manufacturing process. As we look to the horizon of mechanical engineering, CAD/CAM, and machining, it really makes you wonder, as smart factories continue to evolve, how will the integration of AI permanently change tool design? Will artificial intelligence soon be doing all of these incredibly complex nodal geometry calculations autonomously, generating custom 3D models for tools operating in completely dark factories? It's a fascinating future to prepare for sure. Thank you so much for joining me on this deep dive into cutting tool design. Keep learning, keep designing, and I'll catch you on the next explainer.